Hey guys, today is derivatives. So, when you want to find the average rate of change of a function over a specific interval, you calculate the slope, right? So, let's say I want to find the average rate of change of f of x over the domain from x to some, I don't know, horizontal distance that I add to x. Let's call it x plus h, okay? So if I go up to the curve, I'm looking at the point x, f of x, and the point x plus h, f of x plus h. Okay, these are the 2 points on the curve. So if I want to find the average rate of change, I'm basically finding the slope of the secant line. This is a little bit of a vocab review. Do you remember a secant is a line that passes through 2 points on a circle? And then a tangent is a line that kind of just touches right over there. Yeah. All right, cool. Secant, tangent. So I'm trying to find the slope of the secant line. That's going to be the same thing as the average rate of change. And it's over a specific domain or interval. And in this case, it is from x1 and x plus h, okay? Okay. So I want to do the change in y, so that would be the first thing, right? Minus the first y all over the change in the x's. All right, cool. So I'm like looking at this and I'm like, oh wait, some stuff can kind of cancel. I've got f of x plus h minus f of x over these x's are going to cancel all over h. Oh, cool. So I can find the average rate of change between 2 points on the curve at any given point using this formula here. But what if I didn't want to find the average rate of change? What if I wanted to find the instantaneous rate of change, also known as the derivative? Say, what if I wanted to find the slope of the curve or the instantaneous rate of change of the function right at this little x right here, x1. Well, the way you would do it, or the way you envision the slope of a curve, is by drawing a tangent line right at that x value, okay? So the tangent line is just going to touch the curve one time right at the specific x that you're investigating. Well, we have knowledge of average rate of change, we have knowledge of slope, we have knowledge of secant lines, but we don't really have an idea of this kind of instantaneous rate of change. But I do know that I can calculate it using this formula here. Let's see what happens as h, or the horizontal distance between the 2 points, shrinks. So if I have the secant line, he looks like this, right? And I'm trying to approximate or find the instantaneous rate of change right at r. I would shrink, do you see h is right here, this green h? I would shrink that h and get infinitesimally close to r. And then right when h is 0, or there's no distance between the 2 points, I'm finding the slope of the tangent line right at that specific instant. So I would have the limit as h approaches 0. So this is where the limit comes in, right? As h approaches 0, we can't just have h be 0 because then we know that we would have an indeterminate form. But as h approaches 0, I can find the slope of the curve right at that specific point. Okay. So that's the limit definition of a derivative. Okay, here's just some notation that you might see for the derivative. So let's say the original function looks like this. The derivative would look something like this. So let's say I have y equals x squared plus 2x. The derivative notation would look like y prime equals 2x plus 2. The derivative notation could also look like this, dy dx, and we say this is the derivative of y with respect to x, and that would be written like this. If you're given the function in f of x notation, it could look like this. We say f prime of x equals, let's say this was the original, this would be the derivative. Okay, so these are just the notations that you could see for the derivative. Now, let's calculate the derivative, or the instantaneous rate of change. Also sometimes known as the gradient of the function. Gradient is just how, like, IB says slope. We're going to calculate it by hand, and we're going to use the limit definition of the derivative. So the limit, as the horizontal distance between two points approaches 0, aka they get infinitesimally close to one another, we can find the derivative using this formula. Okay? So let's get our original formula. Let's say we want to find the derivative equation for x squared. Okay, let's find the derivative equation for x squared. So we have the limit as h approaches 0 of f of x plus h. Sometimes I like to put this off to the side. So everywhere I see an x here, I'm going to put in an x plus h. So that would become x plus h squared. I would have to expand that out, and I would get f of x plus h is equal to x squared plus 2xh plus h squared. Okay, so I've got x squared plus 2xh plus h squared minus x squared for f of x all over h. Now I know that I'm going to have to do some algebraic manipulation, because if I plug 0 in as is, I'm going to get an indeterminate form. So I'm going to do little combinations here. Ooh, I see that both terms have an h. Let's cancel that h. Factor out that h, and then now I have the limit as h approaches 0 of 2x plus h. I now substitute in that pesky limit, so that way he's not hanging around anymore. And I get the derivative function will be 2x. So if I evaluate that derivative function at any given x value, it will give me the slope of the curve at that specific instant. So let's say, ooh, where you at? Yeah. So let's say I wanted to graph an original curve. I just wanted to graph x squared, right? And then I wanted to graph this guy's derivative. I can do that by hitting tab, hitting d dx. Where is it? Yeah, and then I can just put in the var of the original. So look at this, right? I have the derivative with respect to x of the original function, and I can graph that derivative function. And doesn't that look like the equation of the line y equals 2x? It sure does. So at any given x value, right? Let's say I wanted to find the slope of x squared when x equals 0. Well, if I were to sketch a little tangent line on this guy right here, he would look just like a plain horizontal line touching just the bottom of the parabola, right? Let's evaluate the derivative function, which was saved under F2, at 0, and see what the slope of the tangent line is. It's 0. So the derivative is 0 when x equals 0. Okay, and that's because we evaluated the derivative for x equals 0, and we returned the slope of the tangent line on the original curve. This all feels a little heady, right? So let's just think that we can use the limit definition of the derivative to generate the derivative function, and then we can evaluate that derivative function at whatever x value we want to get the slope of the original function. Okay, so on our calculator, let's talk about derivatives. Finding the derivative using the limit definition is difficult algebraically. However, we can use the calculator to find the derivative if we want. So let's say we wanted to find the slope of this original curve here when x is 3. We would evaluate the derivative function when x is 3, and that will give us the slope of the tangent line when x is 3. So the way that we can do that is we go to our calculator, we open a new page, and we're going to calculate the numerical derivative at a point. So you do menu for 1. We're going to evaluate the derivative. In this case, it says first derivative when x is 3. And then it's going to prompt us for the function. Let's type in the function there. X squared minus 4x plus 1. And we'll get 2. So it says type your function in the box and press enter. You should get 2. This means that the slope of the tangent line at x equals 3 is 2. So let's look at the curve of the original. Yep, he looks great. Let's go to where x is 3. Let's go down to the curve. And if we drew a tangent line right there, the slope would be 2. Okay. So for each function f of x, find f prime of a using the procedure outlined above. Okay, so for question number 1, right, what I would do is I'm going to calculate the derivative at a point with respect to x. Why didn't it prompt me? Oh, I have to go here. Menu for numerical derivative at a point. There we go. And the value is going to be right here, 2, first derivative, and now I'm going to type in the function, 2x squared plus x plus, stop that. There we go. So we would have a very yucky little number, but that's okay. That would be 1.20267. All right, let's try the next one here.
Mommy, quick, we have to watch a movie with Daddy home.
Shh. Okay.
Please, Mommy,
So
let us
then
watch
now
TV.
I have, hold on, that was all in the exponent. I'm making a video right now, honey. You got to get out of here.
Can
Okay.
you make a video?
All right.
Why can't we have?
There
Why can't
we
we
go.
watch TV?
So I would have f prime of -1 is equal to 2.27. Okay. So why don't you try the rest of these, pause the video, and then check your work with the key. Okay, so moving on. We are now going to have our calculators graph derivatives for us, okay? So we kind of just did this, but I went through it very quickly, okay? So we're going to graph f of x equals x squared in a new document. Now in f2 of x, we will give the calculator the command to graph the derivative. And the way that we do that is we hit tab d dx of f1 of x. Okay? We did that, and here we have our graph. That's the original and its derivative. Very cool. So what can we use this for? Well, we know that the derivative function returns the slope of the tangent line at any given x along the original curve, right? It gives us the slope of the function at any given x. So if we pull up the table, we can find f prime of whatever we want, which would be the derivative evaluated at a specific x value. So this column here is the x's. These are the derivatives, right? Evaluated at those specific x's. And we can go through here and see that f prime of 1 is 2. f prime of 4 is 8. All right, what does this tell us about the slope of f of x at x equals 1 versus x equals 4? The function is much steeper at 4 than it is at 2. Let's double check. The function is much steeper at 4 than it is at 2. For sure.
You've run away.
Now, use your calculator skills from exercise 3 to investigate each of the following. Draw a sketch of each situation. So you're going to go through and determine if these are true or false. So for the first one, it says the derivative of any cubic function is a parabola. Well, if we have a cubic function, he's going to look something like this, right? And then let's see if his derivative looks like a parabola. Well, let's graph the original. I need an x to the third, yeah. And then let's graph its derivative. It is a parabola. All right, let's change this just to make sure that it holds true for all. And then look, his derivative changed as well, but he stayed a parabola. So I think that we can confirm that this is in fact true. Now let's try the rest. The derivative of f of x equals e to the x is, let's graph its derivative. Oh my gosh, it's the same. I guess its derivative would have to be e to the x as well. The derivative of f of x equals sine of x. Let's see. Let's make sure we're in radian mode, okay? Ooh, let's graph its derivative. Yeah. Get in there. Stop it. That looks like a cosine graph. My goodness. So this was our original, right? He was like this. He was f of x. And then his derivative was a cosine graph. That's crazy. All right. Now you should be able to do the homework. I'll do one with you just so you know what you're doing. Let's do a harder one. Let's do the radical one, okay? So I'm going to use the limit definition of the derivative to find the derivative function. Then I'm going to check the derivative using a calculator, like the graph part, and then I'm going to see if they match or not, okay? So I would say the limit as x approaches, or sorry, as h approaches 0 of f of x plus h minus f of x all over h is going to be the following. So I would have, let's find f of x plus h off to the side. So I would have the square root of 2 times x plus h. So let's figure out what that would look like. That would look like the square root of 2x plus 2h. Okay. And then that is going to be minus and then f of x is going to be the square root of 2x all over h. And then now this is going to be an indeterminate form, so I have to retcon. Oops. Okay. I got an email. Okay, so now I have this. I would have 2x plus 2h plus, oh my goodness. Oh, good, these cancel. I was like, oh my goodness. This is crazy. Okay. All right. So then now let's see. These cancel. These cancel. I now have 2h over h. Yay, these cancel. And then radical 2x plus 2h plus radical 2x. Okay. And then now I have 2 over the square root of 2x plus 2h plus the square root of 2x. I'm going to substitute in that 0 for h, and I get the derivative is equal to, what just happened? Oh, I thought I stopped my video. I got so sad. Okay, would be 2 over the square root of 2x plus 2 rad x, which would be 2 over, and then I have, oh my goodness. Okay, wait, hold on. This was not supposed to come out of there. There we go. 2 radical 2x. And then these would cancel, and I would get 1 over the square root of 2x. Okay. So now, oh my goodness, I have the derivative, yikes, stop that. I have the derivative is equal to 1 over the square root of 2x. And I'm going to graph and see if that is the truth. What is this thing doing? Oh my goodness gracious, what just happened? Okay, all right. So now I have the original function. I have the original function is the square root of 2x, and then now I would like to graph the derivative function and see if I've gotten it correct. And it is 1 over the square root of 2x. And I'm going to see if when I graph the derivative it lays right on top of that. All right, let's see. So I've got this here, and then the var that I'm pulling from is F1, and they're the same, hooray! So then it says derivative using calculator, they match. And then I would say, do they match? Yes. So it looked like my sketch was like this. This was the original, and then these were the two things, and they were grid. That's it. So you would just have those 3 or 4 problems left to do. I hope this made sense. Sorry for everybody talking in the background.